We are now at question 11, the last question of this CXC CSEC May 2014 General Paper 2 exam video solution. And part A of this question 11 gives us this matrix M, where M is equal to 7, 2, P negative 1. And we are told to find the value of P for which M has no inverse. And when a matrix has no inverse, it is referred to as a singular matrix, and therefore what we really want is the value of P for which M is a singular matrix. Now, a singular matrix is a matrix that has no inverse because its determinant is equal to 0, and this is it. If M is a singular matrix, it has no inverse, and that would be because the determinant of M is equal to 0. And so to find the value of P for which the matrix M has no inverse, we simply need to write an expression for the determinant of M and equate that to 0. Now the determinant of M is equal to the product of the elements on the leading diagonal minus the product of the elements on the following diagonal. The elements here, 7 and negative 1, are on the leading diagonal, and the elements here, 2 and P, are on the following diagonal. And so the determinant of M would be equal to 7 times minus 1, that's the product of these two elements, minus 2P, which is the product of these two elements. And to find the value of P now, we solve this equation. So this reduces to negative 7 minus 2P, because 7 multiplied by negative 1 here is negative 7. And when we transpose to make P the subject, it comes out to be 7 divided by negative 2. And this is obtained by firstly taking this negative 7 onto this side, where it becomes a positive 7, and then we divide by the negative 2. Or we can say we add 7 to both sides first, and then we divide both sides by negative 2. And so P will be equal to 7 divided by negative 2, which works out to be negative 3.5. And so that is the answer for this part. The matrix M has no inverse, meaning it is a singular matrix when P is equal to negative 3.5. And let's move down now to part B. Now part B gives us this pair of simultaneous equations, and we're asked to express the pair of simultaneous equations as a matrices equation in the form AX equals B, where AX and B are matrices. And to do this, we must ensure that in each equation, the first term is a term in X and the second term is a term in Y, and that is the case here. In this equation, the first term here is a term in X, the second term here is a term in Y. And in this equation, the first term is the X term and the second term is a Y term. And the matrices equation for this pair of simultaneous equations will simply be this. This matrices equation is set up simply by observing the values in this pair of simultaneous equations. The 4 and the negative 2 here becomes the first row of the matrix, and the 2 and the 3 here becomes the second row of this matrix. The X and the Y becomes a column matrix here, and then the values on this side, the 0 and the 4, becomes the column matrix. And this matrices equation matches the pair of simultaneous equations because, for example, if we were to calculate the value of 0, that is the 0 here, we would have to multiply this row by this column. And we see that this 0 would be equal to 4 times X plus negative 2 times Y. And that is what we have here. 4 times X and negative 2 times Y is equal to 0. And then this 4 here would be equal to this row multiplied by this column, and that would be 2 times X plus 3 times Y. And so 2 times X plus 3 times Y would be equal to 4, and that is what we have here. 2 times X plus 3 times Y is equal to 4. And so this matrices equation matches this pair of simultaneous equations. And we were not asked to solve the equations, and so this is the answer. But if we were asked to solve the equation, we would want to find the value of X and Y. This matrix actually is the X matrix. A would be equal to this 2 by 2 matrix, B would be equal to this column matrix, and the matrix that we would want to evaluate would be this matrix XY, which is equal to this X. And so we would have to transpose this matrices equation and make X the subject. And by simple matrices transposition, this equation would be transposed such that X now would be equal to a to the minus 1 times B. And that is by simple matrices transposition, because what happens is that both sides of this matrices equation is multiplied by a to the minus 1, which is the inverse of the matrix A. And then on this side, we would have a to the minus 1 multiplied by A, and the product of a to the minus 1 and A would be equal to the identity matrix, and then the identity matrix multiplied by the matrix X would be equal to X. And so we'll be left with a to the minus 1 multiplied by B on this side, and this is what we have. And so now we would need to calculate the inverse matrix of A, and so we can write the expression for a to the minus 1, and this is it. X now becomes 1 divided by the determinant of A multiplied by the adjoint of A multiplied by B. This formula here would give a to the minus 1, which is the inverse matrix of A. And it is 1 over the determinant of A multiplied by the adjoint matrix of A. So we can proceed from here to show the calculation of the matrix X. And this is it. The matrix X, which is the matrix XY, becomes the subject here. And then the determinant of A will be equal to this. That is 4 times 3, the product of the diagonal here, minus 2 times negative 2. That is the product of these two terms. The determinant of A is the product of the two terms here minus the product of the two terms here. And that's what this is. And then the adjoint matrix becomes this. This is the adjoint matrix, which is represented here. And the adjoint matrix of A is obtained by interchanging the elements on the main diagonal, and so the 4 and the 3 here are interchanged to become 3 and 4 here, and then we change the sign of the elements on the trailing diagonal, and so this negative 2 becomes 2 here, and this 2 becomes negative 2. That is, we interchange the two elements here and change the sign of each of the two elements here, and that is how the adjoint matrix is formed. And then now we are multiplying this matrix by the column matrix B. This expression now can be simplified to this. The 4 times 3 here is 12, negative 2 times negative 2 is positive 4, and so on the denominator here we have 12 plus 4, which is 16. And then this matrix is a result of the calculation of the product of these two matrices, and that is 3 multiplied by 0 is 0, and then 2 multiplied by 4 is 8. To get the element here, we are multiplying this first row by this first column, and the element here will be obtained by multiplying this second row by this first column, and so it would be negative 2 multiplied by 0, which is 0, and then 4 multiplied by 4 is 16. And so the result here is 8, and the result here is 16. And then 8 divided by 16 is a half, and 16 divided by 16 is 1. And so this reduces to the column matrix 0.51. And therefore, X would be equal to 0.5 and Y would be equal to 1. And from here, we could show our solution line. X equals 0.5, Y equals 1. But remember, we were not required to produce this solution, and so this matrices equation is our answer for this question 11b. Let's move down now to question 11c. Now in question 11c, we are given this vector diagram, and it shows the vector from O to P such that P is a point 24, and also it shows the vector from O to Q, where Q is a point A2. And we are told that the line OP may be written as this vector OP. And the first part wants us to state the term which is used to describe this vector OP. And this vector OP is the displacement to P from the origin. it is the displacement vector from the origin to P. And the displacement vector from the origin to a point is called the position vector of that point. And so the displacement vector from O to P, which is this vector, is called the position vector of P. And so that is the answer. The term that is used to describe this vector OP is the position vector of P. Part 2 now wants us to find firstly the vector OP, and then the vector OQ, and then the vector PQ. Now, as I have said, the vector OP is a position vector of P, and the position vector of P will have the same values as the coordinates of P, and therefore the position vector of P is the vector 2, 4, having the same values as the coordinates of P. This vector OQ is the position vector of Q, and this vector OQ also will have the coordinates of the point Q, and therefore the position vector of Q, OQ, will be equal to the vector 8, 2. Now this vector PQ is called a displacement vector. It is a vector from P to Q, and this displacement vector PQ can be expressed in terms of the position vector of P and the position vector of Q, and it is such that it is equal to OQ minus OP, and this is referred to as O times the last minus O times the first. In the displacement vector PQ, Q is the last and P is the first, and the displacement vector PQ is O times the last, which therefore becomes OQ, minus O times the first, which is then OP. And we have OP from here, and we have OQ from here. And therefore, this works out to be 8, 2, which is the position vector of Q, minus 2, 4, which is the position vector of P. And when we do this calculation, the result is 6, negative 2. That is, 8 minus 2 is 6, and 2 minus 4 is negative 2. And therefore, the displacement vector PQ is 6, negative 2. And we can show this displacement vector PQ on the diagram. And the displacement vector PQ is the vector from P to Q, and this is it. The displacement vector PQ is equal to 6, negative 2, and it would be such that to go from P to Q, we would have to go 6 units to the right and 2 units downwards. And so that is the answer for that part. Let's move down now to part 3. Now part 3 tells us that the vector OP is equal to the vector RQ. So we are now introduced to the point R, which is not yet shown on the diagram. And so this is a vector equation, and we are required to find the coordinates of R. Now, in order to find the coordinates of R, we need to break the position vector of R out of this equation. In this vector equation, we have 3 points represented. We know the position vector of P, and we also know the position vector of Q. What we don't know is the position vector of R. And therefore, in this vector equation, there is only one unknown, which is the position vector of R. And any equation with one unknown can be solved for that unknown. And in vectors, we solve for an unknown position vector by splitting the vector equation into position vectors. And so we're going to split this displacement vector RQ into position vectors. And when we do that, this is the result. The vector OP comes back here, and then this vector RQ is equal to O times the last minus O times the first. And so it becomes OQ minus OR. And so now we need to make OR the subject. Once we have the position vector of R, we can write the coordinates of the point R. And so to make OR the subject, we're going to take this negative OR onto this side, and it will become positive OR. And then we're going to take this OP onto this side, and it will become negative OP. So let's show that. And this is it. OR becomes equal to OQ minus OP. And since we know the vector OQ and also the vector OP, we can now calculate the vector OR as follows. The vector OQ is equal to 8, 2, and the vector OP is equal to 2, 4. And so when we do this calculation, the result is that the vector OR is equal to 6, negative 2. And therefore, the position vector of R is 6, negative 2. Now we must notice that this vector OR is actually equal to the vector PQ. And we have the vector PQ here on the diagram. And if the vector OR is equal to the vector PQ, it means that OR has the same length and direction as PQ. And therefore, on this diagram, the vector OR will be parallel and equal to this vector PQ. And it will therefore be equivalent to transferring the start of this vector to the point O. And so let's show that. And this is it. And therefore, this vector is OR, and so this is the point R. And we can show that. That point, therefore, is the point 6, negative 2, because this vector OR is a position vector of R. It has values 6, negative 2. Therefore, the coordinates of R will also have the same values, 6, negative 2. Also, we must notice that the vector RQ is equal to the vector OP. That is from here. OP is equal to RQ, and so we can say RQ is equal to OP. And similarly, because the vector RQ is equal to the vector OP, the vector RQ will be equal in length and will have the same direction as OP. And so this vector RQ will be equal to this vector OP, and it will therefore be equivalent to transferring this vector to here. And we can show that on the diagram. And this is it. And therefore, this is our completed diagram. But the result for this calculation is that the coordinates of the point R will be 6, negative 2, because as I said before, the position vector of R is 6, negative 2, and so the coordinates of R will have the same values as the position vector of R. And so this is the answer for this part of the question. Let's move down now to part 4. Now part 4 is asking us to state the type of quadrilateral formed by PQRO, and we are to give reasons for our answer. And so we have to go back to the observations that we made in the previous sections, and this is it. OP is equal to RQ, and also OR is equal to PQ. That is, this side OP is equal in length and parallel to this side RQ, that is from this equation, and this side OR is equal in length and parallel to this side PQ, and that is from this equation. And if we remove this vector line, we will see the quadrilateral PQRO, and this quadrilateral will therefore have two pairs of equal opposite parallel sides, and so we can write that the quadrilateral PQRO has two pairs of equal opposite parallel sides, and a quadrilateral which has two pairs of equal opposite parallel sides is called a parallelogram. And so PQRO is a parallelogram. And so that is the end of this part of the question, the end of question 11, and the end of this production. And as usual, I hope you learned a lot, and
Daddy, you're recording mathematics the easy way for me?
Yes, Kai, but you have to be quiet. Remember, you have to be quiet when I'm recording this stuff, okay?
Yes, Daddy.
And I hope that you will remember that more maths equals better maths, so you will continue to practice hard so you can pass your exams the easy way. I'll be doing more exam video solutions in the future, and so I'll just close now by saying bye until next time.